So this is just the end of our inequality section here, specifically talking about absolute value inequalities. So the way to think about an absolute value inequality is this. Notice what sign you have. Think about this as great or than. Great or than. The reason I say that is because when you say, oh, I have great or, that makes you think or, which is because what you have there inside the absolute value needs to be greater or equal to 5. So that means greater than or equal to 5. Anything greater than or equal to 5, as long as the inside is that, part of your solution. However, if you had, for example, a -5 inside, or a -6, or a -10, or a -100, its absolute value is the positive. So it's 5 or 10 or 100, which is still greater than or equal to 5. So the values that are possible for this is when the inside is greater than or equal to 5 or less than or equal to -5. So it creates two inequalities, 3x plus 2 greater than or equal to 5. Well, that's pretty straightforward. But then you also need 3x plus 2, there we go, less than or equal to -5. So the or gives you two inequalities which have flipped signs and flipped signs on the constant. So greater than or equal to 5, less than or equal to -5. These are two separate intervals. That's why we have the or. Then, now they're just two linear inequalities and we can solve each one. If you want, you can pause and take a moment and solve each one better than I'm doing, hopefully. I've done a lot of videos today. I'm done. Okay, please, go without me here. Okay, so we have 3x greater than or equal to 3. We divide and we get x is greater than or equal to 1. Okay, so that's one of our inequalities. Over here, we're going to subtract 2 and 3x less than or equal to -7. X is less than or equal to -7/3. So if we think about this just a little bit, I can always be helpful to kind of look at a number line here. I don't need to put a whole bunch of numbers on it, but just to kind of remind myself, I've got 0, the 1 will be over here, and -7/3 is going to be over here. What we found is greater than or equal to 1 looks like this. Less than or equal to -7/3 looks like this. So notice, we've got these opposite directions happening. That's what happens when you have the or. So you really want to pick up on the fact that or gives you this inequality here, and it gives you this inequality here. So notice that. The reason I did the number line was just to show you that that's the intervals that we want to do. So I'll do interval notation here. So notice we are -infinity all the way up to -7/3. And that is included, so I should really make sure that that's nice and like that. And then that's unioned with 1 on up, so out to infinity on that. So any value that you put in either one of those intervals is going to make that absolute value inequality true. Now here's the other situation. So in this case, we have less than, I know that looks weird, but it's on purpose. So we have less than. So when you have a less than symbol, think less than, which should trigger you to say, okay, I have an and situation. So the idea behind less than is this. The first thing I'm actually going to do is multiply both sides by 2. If I multiply both sides by 2, which is totally valid, I'm going to end up with this. Okay, so now what we actually have is just something similar to what we saw before, but again, with the less than, not greater, less than. So understand that as long as what is on the inside is less than 8, it's part of our solution. So for example, if I put in 1, you can see that 1 times 3 is 3, plus 2 is 5, absolute value of 5 is less than 8, we're good. However, you could also have a number inside like -4. And if you had -4 on the inside, its absolute value is 4, and that's still less than 8. So when you have less than, you're going to take the inside and say, as long as it's less than 8, but greater than -8. So notice less than creates like this sandwich. Okay, so notice we've got an inequality sandwich here. And if you understand that the inside has to be greater than -8, all that means is you could have a -7, a -6, -5. Obviously, there's values in between that, -4, -3, -2. Its absolute value is going to be less than 8. So these are our boundaries here. And then we just solve this, like normal. We've seen this before, just without the beginning of the absolute value. So we'll have, oh, I need to get rid of that. That's the whole point. That's what I just did. Okay. All right, so we have less than 6, greater than -10. We divide by 3. And it looks like we'll have x is less than 2, but greater than -10 And notice that this is a situation where if you think of, can't draw a straight line to save my life with this tablet. If we think about the number line here, we're going to put 0, we'll put 2, we'll put a -10. And what we see is that x needs to be greater than -10, but not equal to, but it also needs to be less than 2. So notice that sandwich here, we're creating one interval where the lowest value that makes it true is not -10, but infinitely close to -10. And then the greatest thing is not 2, but getting infinitely close to 2. So even 1.999999999 is going to make this true. So we create an interval notation solution that looks like this. And that is section 1.8.